So this is the circuit that we finished up with last time. I wrote this a little bit small to condense this here. This is in your notes from last time. We saw this circuit here. It was put forth to you in the time domain. It's our first time that we transferred from the time domain to the phasor domain. We're going to transfer it to the phasor domain, and then we are going to solve it. And before we're done, we'll transfer back to the time domain. So we're looking for this voltage here. The voltage at this point up here, at that node up there with respect to this, if we were to take that as ground. We went through this process last time putting voltage 1 in phasor form. There was a little sticky point with this sine here. I converted it to cosine by subtracting 90 degrees and coming up with our voltage 2 in phasor form there. Then the loads, the resistors, are pretty easy in time or phasor. The inductance, Z for an inductor, remember, is J omega L. Probably got that beat into you in the laboratory this week. If not, as you write that up, you will. Remember, the lab write-ups for that first report are due on or before the first exam. Probably don't want to wait too long on that, one, because you don't want to be hassling with that when you're working on the exam, and two, it's easy to forget what you did in lab, so I would start writing that up soon. So we were able to calculate the impedance for the two inductors. Remember that our frequency was given up here. That's what that 400 is about. That's the omega. And then the impedance for the capacitor in general was 1 over j omega c, which we oftentimes write as minus j over omega c. And we then came up with the impedance for the capacitor. So what I can do, if there's no questions on this page, again, it should be in your notes from last time, is to take what we found there and put that into the circuit. So I've got voltage 1 in phasor form, I've got voltage 2 in phasor form. What was the voltage 2? This is 150 at minus 90 volts, and voltage 1 was 180 at minus 36.87 volts. Okay, so I put those voltages in, I put the loads in phasor form, and now I'm looking for this voltage here, and I'm looking for the voltage in phasor form. We will find it in phasor form, and I'll have to convert back to the time domain. Well, that was kind of a problem in and of itself, but now it turns to a problem that looks like a node problem, right? Probably node analysis is a good way to do this. You have an essential node down here that I'm going to ground. You have an essential node up here. Two essential nodes are going to give us one equation, so probably node analysis is a good way to go. If we were to do mesh, we'd come up with 3 equations, right? Which would probably be a good check for this. You should be able to do 3 simultaneous equations on your calculator, hopefully. But we'll keep this simple with 1 equation. So I could take this current. I'm going to assume this current here as I1. I'll assume this current here as I2. I'll assume this is all one node. If it was down in laboratory, that would be all one spring on the board. I'll take this as I3. And finally, I4. So I could write with Kirchhoff's current law would give me I1 plus I2 plus I3 plus I4 is equal to 0. Okay, presumably 1 or 2 or more of those are going to be negative. They couldn't all be positive. So I1, now going up here and figuring out what I1 is. To talk about I1, I really need to talk about the voltage that is opposite this, right? So I need to go minus V1 plus V. I'm going to define this as our unknown V. So that's V. So I will have V minus V1 divided by J12. Plus I2, and we're going to have to do a similar operation over there for I4. So if you're a little rusty on this, you'll see this technique again with I4. I2 is easy. What's I2? Simply V divided by 15. Plus I3 is again an easy one. V divided by what? Minus J20. The only trick there is not losing that negative sign, so figure out a way, some parentheses, or you could put it up there. But keep that negative side. And then we get to the last one, and another kind of difficult one. We've got the current there. We need to find the voltage across there, don't we? Which is going to be, you can think while I'm erasing. What are we going to have for I4? We're going to have to go minus V2, right? Minus V2 plus V. So I have V minus V2 divided by J10. Kirchhoff says that's equal to 0. Questions with that? Yes? What's that? Yes, it's plus in there, isn't it? Thank you. Yeah, so that is plus, thanks. Other questions? Yes?
The impedance of a resistor is equal to the resistor. That's a 15 ohm resistor on the left side. Why isn't it J15?
Well, the impedance of a resistor, let me back up here on this other piece of paper. So the impedance of a resistor is equal to R plus J omega 0. So the resistor is the real portion. Okay. To go a little further on this, let's say then the impedance of the inductor, let me make this a little more complicated here, is equal to 0, essentially R, okay, plus J omega L. And those of you that were down in lab say, oh, yeah, the heck with 0 R, it had quite a bit of resistance, didn't it? But ideally, it would have 0 resistance. Okay. So the impedance for a resistor and capacitor is all complex. The impedance, let me restate that. The impedance for a capacitor and an inductor is all complex, is all imaginary, whereas the impedance for a resistor is all real. Other questions? Good. Okay, so we've got this equation. Make my substitutions for V1 and V2. So I have then that I have V over J12 plus V over 15 minus V divided by J20. I can do that with a negative sign, plus V over J10 is equal to, now this was minus V1 over J12, so it becomes positive here, V1 over J12, and this one likewise becomes positive V2 over J10. We're good with that? Now a lot of you probably would have thrown it into the calculator at this point, defined what V2 is, defined what V1 is, ask it to solve it. That's fine. I think I'm going to work on it a little more for the folks that don't have quite as sophisticated a calculator. And again, I keep saying this, if you're not able to get to the numerical answers that we're getting to in here, you need to spend some time with your calculator, right? You got an extra day, right? Okay. What did Martin Luther King say? He talked something about how we shouldn't be judged by the color of our skin, but rather the content of the character. And I think there was a silent phrase in there. You wanted everyone to be able to do phasors on their calculator. Okay. Okay. So use some time. Don't take me being flippant about that. I'd spend some time Monday reading some of his speeches. The letter from the Birmingham jail is always good. Read that. Then spend some time working on your phasors on your calculator. So let me rearrange this a little bit. I will have, when I substitute my V1 in there, flipping sides on you, I have 180 at minus 36.87 divided by J12. I'm going to add that to V2, which is 150 at minus 90 divided by J10. And then I have to divide that by the whole thing there that I factored out. So if I take this equal to V, I can put what I factor out of V, which is 1 over J12 plus 1 over 15 minus 1 over J20 plus 1 over J10. So let's see what that's equal to. I'll write it in numerator over denominator form to give you some help with this if you're working through this. maybe I've made a mistake already. Okay, so for the numerator, I get 26.83 at an angle of minus 153, minus 153.4. I'll work on the denominator now. .1491 at an angle of minus 63.4. You divide those, you get 180 at minus 90. Okay. So we could say, if we wanted to, that the voltage V is equal to 180 at minus 90 volts. Anyone else get that answer? Few people? Good. Like I say, if this is not working out for you in your calculator, write this down. I think this answer is right. I'll be posting this lecture, the PDF. Grab the PDF. Go home this weekend. Keep pounding on your calculator until you can make it work out. Okay. If you're mechanical in here and you have something less than a TI 89, yeah, you can probably make that work out. Get out of the class and try not to remember this stuff. If you're an electrical, this is just the beginning of a long series of this. So if you've got a calculator that's really hampering you, you may think about upgrading, because you'll use it again if you're an electrical. Now, I don't know that we've answered this very well, because we were really looking for the answer in the time domain. Remember that we asked the question, what was V of t, on the previous page, or on your lecture notes from last time. So let me go back to that. Let me write that in terms of V of t. I could say that V of t was equal to, the magnitudes is 180 times the cosine of, what do we have for our frequency? 400 times t. That was the omega. 400 times t, and then I have minus 90 degrees, and that's volts, and that would certainly be a fine answer. Although, remember, they kind of played a trick on us and gave us one of the voltages, voltage 2 in sine. This is really begging me to turn that around on them, isn't it? I could say, or it's equal to 180 times the sine of 400t, and I wouldn't have any phase shift then, would I? Okay, so you could do it that way. So if you're looking at someone's solutions or something and it doesn't look like what you've got, check the trig operator. Maybe they've switched it on you. Questions of that? A real good solid problem, converting from the time domain to the phasor domain, doing the problem in node or mesh or whatever, and then finally converting the answer back to time domain. Okay, so we're right at finishing up Chapter 9. Probably some things that we should talk about as we're finishing up Chapter 9. Not that we're going to not bump into them again, but just to make them clear, we talked last time about the impedance triangle for an inductor. What's that look like? Remember, inductors have probably some j omega L and some resistance, so that impedance is going to look like this, the impedance triangle. You have your j omega L here, you have your resistance, and you get an impedance triangle that looks like that with your angle of your impedance. Okay. And I think you all found out that the resistance was larger than the, that's not a triangle that's very far out of scale for what you had in the laboratory. The resistance was the larger portion for the inductor. For a capacitor then, usually the capacitor has a lot of capacitance and then not much resistance. So we have minus J over omega C. We have the resistance, so we would write it like this, probably very little resistance, a lot of capacitance. So there's R minus J over omega C. We get something like that with our angle in there. The impedance triangle for a resistor is kind of boring, isn't it? There's your impedance triangle. So, which are good things to think about in general. There are also required of you in your lab. So the phasor diagrams then, remember that we would oftentimes talk about a voltage and current diagram. Maybe when we get into three-phase, we'll talk about multiple voltages on a diagram, but usually at this point we talk about one voltage and one current. So I think with our inductor, following along with this theme with the inductor here, what do we have? We had our current like this, and then what was our voltage doing? Let's see. What's this got to follow? Eli, is that right? So if I have something like that, I had better have my voltage there, right? Okay. Whereas this one for the capacitor, it's going to look like what? If I were to have my current here, and there's nothing that says that I have to have my current there, but a lot of you did that for the lab, and that's fine. You probably had your voltage something like this, didn't you? So we had ice here. The current was leading the voltage. Then for the resistor, we had the current maybe something like this. And where was the voltage hanging out? Right there. They were both in phase. Okay. And the phasor diagram is important because this angle in here, what is that? That's theta, which is the same as on the impedance triangle. What's this angle in here? That's theta. And we'll see that angle again when we get into power. Look at the power triangle. Yes?
Still on your capacitor phasor diagram,
Mm-hmm.
you're trying to figure it out when current is on the positive x-axis.
Right here?
Yeah.
Okay.
I thought you didn't count that as coming to that first, and then figure whether ice or Eli.
Okay. I mean, if I'm so the question is about what is leading and lagging. If I were to think about traversing this way, what one do I come to first?
Right.
Okay, I do come to I. How about this one? If I were to come to on this one, if I were to come around like that, I come to V.
I thought you started from positive x-axis.
Like that? Okay. Oh, I see. I think I understand your question more. If I'm going to start right here, why don't I say I come to I first? Well, as I start around this way, I have to ignore I and come over here. But if I start around here, I will get to I first. Okay. In Chapter 9, your author goes through a lot of this, and that's a very valid question. Just keep practicing on it.
So with that graph right there, with V, the voltage, it's in on that graph, it's in the fourth quadrant.
Okay.
So we have to start not at the positive x-axis, but from the first, from the
It really, I mean, the location doesn't matter. It's the relative position. So let me come down here and rotate this thing a little bit. What if I come up with I like this and V like that? What's leading? I. It's exactly the same capacitor. I mean, in lab this week, I convinced some of you to take one of the voltages as 0 and the other one reference to that. We could have really taken the first one as some odd angle and then referenced the second one to that, and you would have got a picture that looked like that. Because again, what we're interested in is the difference between them. Okay. So keep working on the impedance triangles and phasor diagrams. We can also use phasors on operational amplifiers. I'm not going to go into that, but you could have a op-amp that has impedances on it. And you're going to use the same linear assumptions that we talked about last term. So if that ever comes up, you can use that. Norton and Thevenin models, I'll talk a little more about that. We're going to get into that when we get into power, because we're going to talk about maximum power, which is going to be a little different than last term, but the models themselves are not going to change. For instance, if I have a Thevenin model, what was that? That was some voltage source, V Thevenin, that was in series with some resistance. We'll call it impedance. We'll call this Z Thevenin. And what is Norton's model? That was some current, I short circuit essentially, that was in parallel with some, well, it used to be resistance, but now is Thevenin impedance, right? And how can you relate these? You know that these observe Ohm's law, that V Thevenin is equal to I short circuit times Z Thevenin. So your source transformations work just as well in the phasor domain. Questions on that? Well, on to Chapter 10 in power, and like I said, that was a fairly easy thing. Watt's law, using Watt's law last term with DC circuits. With AC circuits, it's always changing with time, so it's quite a bit more complicated, and probably the most complicated part of it is just all the terminology. We're going to have instantaneous power, we're going to have average power, we're going to have real power, reactive power, quadrature, complex power, lots of different things. So one of probably the best things you can do, even if you're not a real reader, you don't like reading the textbook, Chapter 10 may be one that you want to try and read the textbook, or at least spend some time with a highlighter and highlighting those terms that we will go through, because we're going to be using those. The math is not all that different, but trying to keep up with the terminology and what's meant by average power versus complex power, that'll probably be more difficult, and I'll try and keep you up on that as we go. So Chapter 10, instantaneous. We'll start with instantaneous power. We don't necessarily use instantaneous power very much, other than for help us derive average power, which we use a lot of. So let's say if I start with instantaneous power, I'm going to do this in the time domain. So I could say that some voltage in the time domain is equal to some magnitude times the cosine of omega t plus theta. We like theta for our voltage. And I of t, some current in the time domain, is equal to the magnitude times the cosine. We'll base it on the cosine. Omega t plus phi. We like phi for the current usually. So if we talk about instantaneous power, we can say that instantaneous power is equal to the product of the voltage times the current. Seems pretty straightforward, really. I'm not venturing very far from Watt's law. So we can say that this is making the substitution for these, Vm times the Im times the cosine of omega t plus theta times the cosine of omega t plus phi. And I'm going to remember a trig ID here. So I'll put this up here, trig ID. that the cosine of alpha times the cosine of beta is equal to 1/2 times the cosine of alpha minus beta plus the cosine of alpha plus beta. Okay, so that's our trig identity. You may vaguely remember that, may not be real comfortable where the pluses and minuses are, but I think that's correct. So I'm going to look at this and I'm going to say, well, hey, this looks like alpha. I'm going to look at this and say this looks like beta. So I could rewrite this and say then that my instantaneous power is equal to Vm Im divided by 2, I've got that half factor in there, times the cosine of theta minus phi plus the cosine of 2 omega t plus theta plus phi. So that's using that trig ID. Let me double check, make sure I've written that down correctly. I have. A couple of things we might notice on this. This is not a function of time. Okay, and for now, I guess that's just kind of a hum. That's interesting. Okay, so that's going to save us a lot of work in a little bit. But there's your instantaneous power. And like I say, I think you maybe got a homework problem where it asks you to do the instantaneous power. I'm going to do an example with instantaneous power, but we don't use it very much. You don't pay for instantaneous power. We're not going to talk too much about it. But what we will use it for is to help us deal with average power, which becomes very important. So questions with instantaneous power? So let me set this aside and move on to average power. And here we go with the names. Sometimes we call this real power. Okay, and that's real power in terms of it's a real number. Okay, it's not like you might see someone driving at 300 miles an hour. No, that takes real power. Okay, we are much more specific in this term here. This is real power because it is a real number. So we use the term average power and real power interchangeably. Probably for our work now, we're better off calling it average power. So let me talk about average power. So I'm going to say average power, we're going to say is P. I'll use a capital letter, not a function of time. I'm going to say it's 1 over the period times the integral from T0 to T0 plus T, the period, of the instantaneous power. So just like when I take an average of some test scores or something, I add them all up and divide by how many there were. Here I add up all the instantaneous power and divide by how long it acted. That should give me the average power. So conceptually, hopefully not too difficult there. So I make my substitution. Things get a little uglier looking. 1 over t times the integral from t0 to t0 plus t, making my substitution for the average power. So I'm going to go back to the last slide. If you can call this a slide or piece of paper or where it is in your notes. And I'm going to go get this thing. We said one of the greatest purposes for instantaneous power is to help us derive average power. So I'll substitute that expression in there. So I'm going to have Vm Im divided by 2 times the quantity, the cosine of theta minus phi plus the cosine of 2 omega t plus theta plus phi. And don't forget the dt. Okay. Oh, that looks ugly. Not a good way to spend Friday. Oh, we got, what, 16 minutes? That could be a mess. But remember what we say. We said this was not a function of time. Not a function of time. This is a function of time. I mean, this is cosine wave, isn't it? So what if we add up a cosine wave over one period? I mean, you don't have to go with me on this little mental experiment here. I mean, you could put this into a computer algebra system or brush up on your integration and go through this. It'd be kind of an ugly process. But I'm kind of lazy, so I want to try and think my way through this if I can. So if I look at a cosine wave, what is its sum over a complete cycle? Yeah, it's 0, isn't it? We'll sum it to 0. So this is going to contribute 0 to this. And if I look at this, this isn't a function of time. That's another way of saying what? Constant, essentially, right? So I can make this a lot easier. This solution then becomes what? That the average power, maybe we'll say average power is equal to 1/2 times Vm times Im times the cosine of theta minus phi. Okay. And that's one expression for average power. When we start talking about RMS or effective power, we'll have other expressions, but this one certainly probably is worthy of a box or a arrow at this point. Now there's some important things here. If I were to go a little further, I could say that this is 1/2 Vm Im, so the magnitude of the voltage, the magnitude of the current, times the cosine. What's the difference between theta and phi? Now, if we go back and we look at our Phasor diagram, so we've got this, we have this current here, I, and we had this voltage, if it was, let's say, an inductor, and the angle for the voltage, that's theta, minus the angle for the current was phi. That gave us that angle there. What did we say that was? That was the impedance angle, wasn't it? So we could really write this as theta sub z, where just plain old theta is the angle on the voltage, where phi is the angle on the current, but theta sub z is the angle of the impedance. Yes? The 1 over t? Well, it didn't matter because this was a constant, right? Yeah. What's that? Well, this is, you agree this is a constant, right? And this was a constant. So I got to take those out. So then I have the integral of 0. Okay. Okay. So this is worth looking at. So there's implications of this. If I have a resistor, so for a resistor, what is this power equal to? Average power is going to be equal to 1/2 Vm Im, isn't it? And you might say, well, I'd expect it to be Vm times Im. Where did that 1/2 come from? That's because we've cluttered things up with RMS and whatnot, and we will soon talk about that next week. What if we have for a inductor, and I'm talking about a pure inductor, a theoretical perfect inductor, or a capacitor for that matter, and capacitors are a lot closer to perfect to begin with. I said this is equal to the impedance angle here, theta sub z. That was equal to 0, right? So what's cosine of 0? 1? Is that right? Yeah. Cosine of 0 is equal to 1. So that's how I got this. So over here, what do I have? I have that theta sub z is equal to plus or minus 90, right? Plus if it's inductive, negative if it's capacitive, plus or minus 90. So what's the cosine of plus or minus 90? 0. So for an inductor or capacitor, either one, what's our average power? 0. Well, there must be some cost to this. There indeed is. That's why we're going to have to talk about complex power and other things. This is just one way of measuring this. Okay. So the conclusion here is that what? Only resistors dissipate average or real power. That's worth an exclamation point. So if I have a circuit with a whole bunch of stuff and a lot of inductors and capacitors and whatnot, and someone says, find the average power that's dissipated, do I have to worry about the inductors? Do I have to worry about the capacitors? No. Let's look at resistors. Only resistors are going to dissipate average or real power. Okay. So with that, when we get together next time, which is going to be a while, isn't it, I guess? Winter term is always like this. Particularly since we missed day one, right, to a snow day. We're always making up Mondays, it seems like. We get through MLK, we'll try and catch up, we'll get caught back up, and then we got President's Day and whatnot. But what we'll do next Wednesday then is we're going to come in and we're going to look at this problem where I've got some voltage, I've got some impedance, and I'd like to find the instantaneous power, and I'd like to find the average power. So this will be in the PDFs. I'll put it up there, but we will tackle that next time. You can grab a PDF and solve it beforehand if you want to. I'll see some of you on Tuesday for laboratory. Make sure that you come to that. We'll be back in lecture on Wednesday. Take care. Have a great weekend.